Okay, so I'm going to run through some of the calculations for the iodination of acetone. I'm not going to do every calculation, but I will get you a very good start on this. So here is my data. You're going to have a different one. You have 53 seconds for this and different times from these others, but notice we only did one run. But I'm going to use my own numbers. That way you have to do your calculations yourself. So we have 40 seconds, 20 seconds for the second experiment, 20 seconds for the third, and 80 seconds for the fourth experiment. Then I'm just going to go through the calculation sheet. It explains what everything, and it asks you to do these certain calculations. So that's what I'm going to do. I'm just going to go right through this. So make sure that you have your lab sheet ready, the document, and go to the calculations. And it says the first thing they want to know is the total volume of all the solutions in the flask for the experiments. Well, that is given here. This is 6 mils, 3, 3, and 3, that's 15. Then 3, 6, 3, 3, that's 15. It's always 15. So when we do the calculations, everybody will get 15 mils. So everybody puts that value in. Okay. So we go on to the next part of the calculations. They want to know the initial concentrations once the solutions are mixed in the flask. That's important because we start with stock solutions, but as we put the volumes in, the different solutions, they dilute each other. So we do this calculation. Experiment 1, we start with the acetone. It was 3 mils, and if you look on the front page of your lab report, it's 2 molar that we started with, a stock solution, and then we diluted to 15 mils. And that makes it 0.4 molar for the acetone for experiment 1 when the reaction started. HCl, same thing, 3 mils, 2 molar, 15 mils it was diluted to, so this is 0.4. Iodine was 3 mils, but it started at 0.02 molar, but then it was diluted to 15 mils, so it's 0.00400 molar. So what we would do is put those values in here, and everybody has the same values for this. So you can write these right onto your sheet. Okay, and then I'll do experiment 2, and I think from there you should be able to take it. Look at the volumes. What we're looking at here, is from this table. Looking at these volumes, 6, 3, and 3, 6 mils for the acetone. So you can see the calculation now changes for acetone. It's now 6 mils. Everything else is the same, so now it's 0.8. So we doubled the volume, we doubled the concentration. For the HCl, it stayed the same. And for the iodine, it stayed the same. That's exactly what we were supposed to do in the experiment. We only changed one thing at a time. We doubled the volume, we doubled the concentration. So if we do put those values in here, we end up with 0.8 molar, 0.4, and 0.00400 molar. And when we go to experiment 3, you'll double this, so this will be 0.8. And then for experiment 4, you'll double this, and it'll be 0.008. But I'll let you do those. We'll go on to the reaction rates. Okay, so for the next part, we're finding the rates. If you look at the calculation sheet. So the rate is going to be the initial concentration of the iodine. And that's why finding the initial concentrations were so important. Initial concentration of iodine divided by the time, the final time, because it was final minus initial, but the initial is always 0. So if we know the time that it took for the reaction, we divide that into the concentration of the iodine, we have the rate. So for mine, your number is different. Your times are going to be different here, but actually these concentrations are going to be the same. So for experiment 1, we have 0.004 molar divided by the time, and this is our rate, or my rate. Yours is going to be slightly different. And then this is going to be the rate. Notice the time changed in experiment, currently just an experiment 2. So we have a difference, and notice my numbers are really nice, but yours won't be very far off from that when you do them. So let's put these values into the sheet. So I would need to finish this out. You should be doing that, but I'm just going to leave that. I'm just trying to show you how to do the basics here of each part. So this become this, and then we didn't do this, and we certainly didn't do the average. And then experiment 2, this should be here. And I'll leave you to do the top part. So you'll need to do this one and this one. So you'll use your concentrations we just found for experiment 3 and 4 for iodine and divide by the times for those experiments. So next thing to do is to find the orders of reaction. I'm going to show you how to find A, and then B and C shouldn't be too tough to do. Here's our rate law, and each experiment has its own rate law. All you have to do is put in the values. So I put in the rate for experiment 1 was 1 times 10 to the minus 4 molars per second, and that's because it's right here. We just calculated that. Here are the concentrations for experiment 1, and that's what we have here, 0.4, 0.4, and 0.004. Experiment 2 had a different rate and had a different concentration of acetone, but everything else was the same. So we know a lot, but we're missing the value of K. We'll find that at the end. We're missing the value of A, B, and C. So this is an initial rates method problem. So if we have experiment 1 and 2, we can find the first order of reaction, A. So to find A, we take the rate of experiment 2 over the rate of experiment 1. Now it could have been the rate of 1 over 2, but in this way we end up with powers of 2. But if you want to do with rate 1 over rate 2, no problem. Just you're going to end up with powers of 1/2. Okay, so here I take this information, this rate law and this rate law. I divided this rate law by this one to get here. Now let's see what we get. Well, this reduces to 2. The K's cancel. This is 0.8 to the A, and this is 0.4 to the A, so those don't cancel, but 0.4 to the B and 0.4 to the B. Whatever B is, we don't know what it is, but this is the same thing, so these cancel. 0.004 to the C and 0.004 to the C, those cancel as well. So we end up with 0.8 over 0.4, each to the A, so we can do this, and 0.8 divided by 0.4 is going to be 2 to the A, so 2 is equal to 2 to the A. So what does A have to be equal to? A is equal to 1. When you do your value, your calculation, you may not end up with a nice integer like that, but if you ended up with, say, down here, 1.1, well, that's going to be, you're going to change that to 1. It has to be an integer. If you end up with 0.8, 5, then that has to be changed to 1 as well. So if you had 1.93, then that would be changed to 2, and so on. So make sure that your values of A, B, and C are integers. Okay, so that's what you want to do there. For finding B and C, you're going to take the rate law for the experiment 3 divided by the rate law for experiment 1. For C, you take the rate law for experiment 4 divided by the rate law for experiment 1. And so you'll be able to find those values. And then the last thing that you do, once you have once you have A, B, and C, and let me just finish up here with what I've done. I found A for mine was equal to 1, so I just write it here. So make sure that you make that an integer. That's the only way you'll get marked down for this part is if you put in a fraction. It has to be an integer. Okay, so to find K, now notice I asked you to find K for experiment 1, 2, 3, and 4. So what you're going to do, once you know what A, B, and C are, I now know that A is equal to 1. I'm going to figure out B and C. I won't do that, but that's what you want to do. That's what you'll do. So you'll know for experiment 1, these are the concentrations that go in here. This is the rate. And then we'll know what A, B, and C are. The only thing that's left over is K. That's the only thing that you don't know. So you solve for K, making sure they use the correct units, and that'll go here. For experiment 2, this number will be different, and this number will be different. A, B, and C will be the same, but just put in all your values and find your K value for experiment 2, and then 3, and then 4. And what you should find, since it's a constant, that they should be pretty close to each other, even with the experimental error. Okay, and then that is it. That's all the calculations that you have to do.